want to thank the sponsors of MassSave for supporting our monthly meeting and share some information about their programs. As you'll know, MassSave is a coalition of our state's utilities that are working to support energy efficiency, and MassSave has a really robust set of incentives and support for passive house building. Whether you're adhering to PHIAS or PHI standards, all you need to do is email ICF, the program administrator, to get started. If you're interested in single family building, the incentives start at $25,000. And for multifamily building, the incentives are at $3,750 per unit. And there are various adders as well. And again, there are emails here on these slides. There are also subsidies for training. And so you can contact ICF at passivehousetrainingma@icf.com. And Passive House Massachusetts is also here to help you navigate your passive house building experience. So please feel free to get in touch with us at contact@phmass.org. I'd also like to thank all of our PHMass members, many of whom are represented in the room tonight, whose contributions allow us to do this important work. I'm so excited to welcome John Loercher here. He is the owner and lead consultant at Northeast Projects, LLC. He's also the director of building science program at Rensselaer Polytechnic. And as if that weren't enough, he's also building science consultant and educator with PHIAS. So it's hard to find someone with more affiliations or qualifications to deliver tonight's talk on inside versus outside. Let's give John a big Massachusetts welcome.
All right. Thank you for having me. It's really nice to be here. I will just add, I actually do have one more hat. Is that I'm the current president of the PHIAS Alliance New York chapter. So I have a little bit of like a selfish motive here in that I'm about 10 minutes outside of Massachusetts, and I'm always a little jealous of what's going on here at Passive House Massachusetts. You guys do a really wonderful job with all of your events. I'm actually learning about live streaming presentations and all that, so we're hoping to do a little more in New York. All right, just gonna get rid of this. Okay. Cool. So inside, outside, this presentation, I was just telling a previous student of mine, is basically a continuation or like a research project that I've been toying with between my work at RPI, different scholarships and kind of research initiatives, and now folding it into the CPHC training at PHIAS. So I'll just go through some of these things quickly. Essentially, what we're going to be doing today is identifying and explaining some of the common challenges, specifically in identifying the passive house enclosure or the passive house envelope, depending on what terminology you like to use, within big buildings. So we've seen a lot of this in smaller single-family buildings, kind of common discussion, but we're trying to kind of collect strategies that are being seen in larger buildings as we're seeing multifamily residential really take off, especially in places like Massachusetts. But even as we're seeing in the PHIAS non-res summit that just occurred, we're seeing a lot of larger non-residential buildings happening as well. The second learning objective here is we're going to look at some real world case studies. So this is based on work that's actually complete, final certified projects. We'll go through some kind of technical guidance. So even though we're not necessarily showing like the same project case studies over and over again, the idea is kind of to abstract some of these different inside-outside principles so that we can apply them to different projects. And then talk about how this, how the PHIAS certification process really factors into this as well. Because there's a lot of details about what you choose to be inside, what you choose to be outside, how that affects design processes, verification processes, et cetera. Construction phasing as well is a big one here. Okay, so this is the slide that gives me the most amount of anxiety because there's been so many people that have actually contributed to this, and I just want to make sure everyone is, properly accredited. As I said, this was part of redoing the CPHB curriculum and the CPHC curriculum, which will both be released August-ish. We have the phase one is an in-person for the CPHB. That's actually going to be released this upcoming July, and that will be in Seattle. And then the first virtual classes of this new curriculum will be coming out in August. So please look out for that. The new curriculum is really top-notch. And a lot of it is because we're not just focused on small buildings anymore. Right, so that's like the number one comment from CPHC students is like, okay, enough with the Larson trusses, enough with the, you know, tiny single family buildings. We need to learn how to do big buildings now. And there are a lot of differences between that. Michelle was a contributor. James Peterson was a contributor. A number of other people gave us their time and spoke about project experience to, you know, kind of feed into this whole presentation. Okay, so now for the actual content. First, we just need to go through a couple prerequisites to get a little bit more specific with our language when we're talking about some of the issues. From there, we'll go into ground conditions, vertical shafts, and exhaust ventilation. So these are basically the three categories that I'm using to pull out some of these inside-outside trade-off decisions. Okay, so first, what are we talking about when we're speaking about the actual boundaries? There's a number of different boundaries. If you were in the CPHC, CPHB classes, we're going to speak about thermal boundaries. We're going to talk about air control boundaries, vapor control boundaries. Then there's the FIAS certified boundary as well, right? So it's really important to know well, first of all, to be precise about which one of these we're speaking about, and then knowing how they overlap or how they don't overlap in the process. We need to look into air tightness a bit more specifically because there's actually different ways that we're measuring air tightness on site. According to the FIAS certification guidebook, we have a durability test as well as an operational test. So a lot of the things we're going to talk about, like dryer exhaust, et cetera, will have different testing protocols depending if we're looking at it from a durability perspective or an operational perspective. And then lastly, a really important thing is in big buildings, in all buildings, we deal with stack effect, essentially buoyancy driven ventilation or airflow because hot air rises. That becomes enough of a thing in large buildings that we actually have to start speaking about it a little bit more. So we're going to talk about that as well. So first, the boundaries. This is actually from a case study project that I had worked on in Yonkers. It's a 60-unit multifamily prefabricated project called Lamora Senior Living. We can see the different boundaries are actually drawn here. So we have the thermal boundary on the left. We can see it's really incorporating the entire project, but we also have thermal boundaries between these kind of out of certified enclosure spaces, right? So you can see in the middle diagram here that this isn't working, but there's some spaces on the ground condition that we did not include in part of our FIAS certified enclosure. One of them was a crawl space, the other was a mechanical basement. So even though they're not in our FIAS enclosure, it doesn't mean we're necessarily off the hook for those. We still need to insulate, air seal, et cetera. So now we have these kind of primary and secondary, maybe even tertiary boundaries that are all interacting. And we need to make sure that we're tracking those both through design. So how are our details being drawn to communicate this? How is our construction being phased to make sure that these things are continuous where they need to be? And then how are we verifying those things? And this is where it gets really important to plan and really think in 3D. We've been seeing more 3D thermal bridge analysis, which is really amazing. But I would say we have to take an even further step back and actually look at the kind of massing of our buildings and the programs, how they fit together to really understand, okay, where is that mechanical room that's outside of the enclosure? How does that connect to a trash chute? How does that connect to the elevator or not connect to the elevator? So we get these, you know, this kind of complex Tetris game, especially if you have not straightforward ground conditions that really need to be kind of tracked throughout all of this. Okay, so the next thing that we're defining, as I said, was that air tightness. Most people in the kind of single family world aren't really worrying about this so much, except for the FIAS raters. I think this gets even more emphasized as a concept in larger buildings, because as we start to add more appliances and things that can actually be taped off in certain circumstances, that can add up to make a big difference in our building air tightness reading. So we have our operational test first, and all of this is defined in the FIAS certification guidebook, section C 2.3, if you're interested. The operational test is for everything in its natural position, right? So nothing can be taped, everything has to be how it is. This gets really interesting when we're talking about like appliances, like a direct exhaust dryer, because if you don't have that purchased yet and installed, you have to now leave that duct open for the testing, versus if you have it installed, you might be able to actually rely on the air tightness of the dryer itself to improve the overall air tightness of the building. Yeah. We also have our durability test. So this is the tape test that we're going to hear about from our FIAS raters and verifiers. This is also what we're using for the WFI or the FIAS targets. So it's important for the CPHCs to understand that the number that we're plugging into WFI at the end is actually based on that durability test, which is our taped test. Right, so having that number, especially in a large building, these two numbers could be actually quite different. And we need to know as CPHCs which one of those we're pulling in to our energy model to show FIAS compliance. Okay, and the last prerequisite that I want to speak about is the stack effect. This is a section from 425 Grand Concourse. So you can imagine any continuous vertical shaft in a building like this is going to be dealing with some degree of stack effect. This is based on essentially airflow from over a vertical shaft and a difference in temperature between the top and the bottom of that shaft. Right, so you can see in this kind of basic diagram, we get some interesting physics in the building relative to these open shafts, but also that we're potentially fighting against in our ventilation systems if we have a centralized ventilation system. So in a building that is very leaky, this is something we're going to have to kind of tackle a little bit more. The good thing about a FIAS or a passive building in general is going to be that we're already focused on air tightness. So the less infiltration we have, the less a natural stack effect that we're going to have to battle against. It's also important to show that the stack effect isn't going to be a uniform effect that's applied to the whole building equally. It actually will have positive pressure in some areas, essentially the top half of the building, and negative pressure on the bottom. So there's going to be certain exchanges or certain interactions that happen as you're going floor to floor through the building. And that magnitude of pressure might not be so bad in the middle of the building, but it might be something that really is causing a problem towards the top, right? So you can imagine you put an ERV on the top of this building and you're ventilating all the way down to that first floor. At a certain point, you're dealing with going against positive pressure, and then you hit another point and eventually you're dealing with negative pressure, right? And I'm not an engineer, so these are just the kind of basic fundamentals here, but you can imagine how this would become an issue in a project. Again, passive house buildings are generally less susceptible to this in general. But we will still open windows. We're going to be dealing with elevators going through your FIAS enclosure down into a parking garage. And we need to be aware of this effect. And it's only going to get worse in more extreme environments. So a milder environment or outside kind of temperature range, you're going to have less stack effect. If we have a lot of internal heat gains and a very cold temperature on the outside, we're going to deal with more stack effect. So it's going to be very climate specific, just like all the other kind of FIAS protocols. Okay. So now those are those prerequisites, right? The things that we need to just define in order to discuss the rest. The first main category that I want to go into is our ground conditions. So this is basically starting at the bottom and working our way through the building enclosure. Bringing back some of those diagrams from earlier, if we look just at basements and crawl spaces first, we're seeing in more and more multifamily larger projects that there's many spaces that are cut outside of the FIAS enclosure, the certified enclosure, within the building. This might be, occupant storage spaces, bike storage, some mechanical spaces potentially, garbage chutes and garbage compactor rooms. In this particular project, Lamora, we had a crawl space because it was modular. So we needed these piers for the modules to sit down on. So again, going back to that FIAS enclosure was really important. And then essentially when you conclude that you're going to cut a space out of the FIAS enclosure, it's really easy to think, okay, I'm off the hook, right? Like we don't have to worry about this space, but that's actually where you have to start to defer to some of the co-requisite requirements. So you're still subject to both Energy Star and EPA Indoor Air Plus requirements for these out of enclosure spaces, right? So even from a verification perspective, the FIAS Radar Verifier still has almost the equal amount of work to be doing in these spaces. And that's where we start to get some of these redundant barriers. So we have the FIAS airtight or the FIAS thermal boundary in the ceiling between this mechanical space and the residential units above. But we also still have to maintain our thermal boundary going down those foundation walls under that slab. Again, we're not necessarily off the hook. The Energy Star multifamily requirements aren't too burdensome. They do have a code minimum value, and if code doesn't prescribe that, they say it must be at least R5, right? So you do have to do something regardless of what building energy code you fall under. The two more significant things is that you still have to pay quality attention to how your insulation is installed. Right? You can't just kind of do like a quick and dirty job down there. And you still have to meet the Energy Star requirements for air tightness. So these are all going to be areas of additional detail and concern. And then on top of that, we still have the EPA Indoor Air Plus as well, right? So again, not a FIAS certified space, but we need to deal with that air tightness limit, compartmentalization, duct leakage. And then there's actually some pretty specific requirements for moisture control and humidity control and ventilation. Even in the case of this project, we just have this 3-foot crawl space with a bunch of piers, but now we have to condition it. We need to dehumidify it, insulate, vapor seal. So it's like the trade-off is, was it really worth it to do that? The conclusion's kind of still out. Okay, so those are for some basic conditions. Obviously, we need to deal with podium construction as well for large buildings, a common typology. The first one at FIAS that we really saw was, well, actually, no, it's not the first one, but 425 Grand Concourse was where this really started to come into, the perspective is something we really needed to figure out a little bit more. The podium construction is, or pedestal or platform, podium, some combination of those words is essentially when we get division in structure, right? So there's fire resistance benefits in that we get a very robust structure on the bottom that's fire resistant, and then we can switch to a lighter construction type up above, which is going to be more cost effective. So typically we'll see on the bottom in that fire resistance section, something that's very conductive as well, like concrete or steel, right? Whereas we're getting our more kind of standard, maybe wood, thermally broken, kind of more thermally durable details up above. And we're essentially given this trade-off decision where we either have to insulate below that podium or we have to insulate above that podium. And it has pretty significant impacts on how we actually go about and detail this. And I knew Michelle's project was in here. Finch Cambridge is on the right here. And then on the left is Barry Farm, which was contributed by Michael Hindle. And you can see the dashed navy blue line here is the podium slab. And then the red dash is where we're actually pulling that insulation down to interact with the slab itself. So we have to deal with utilities that are potentially either interfering with this insulation space or penetrating through that insulation space. Essentially, either way is not totally perfect. There's going to be certain transition details that you have to deal with on either side. Again, how to penetrate and seal, especially considering those fire ratings. Dealing with corrugated steel deck, that's not necessarily like a flat plane, right? But you're dealing with that, again, that kind of thinking in 3D. Structural alignment. So can we actually even design a building that has a structural offset when we transition from the top of the podium to the bottom of the podium to help reduce thermal bridging? All of these kind of three-dimensional thinking aspects really start to play into these decisions. Right, so insulating on top will certainly simplify our air sealing and our thermal continuity. And it tends to be more forgiving with thermal bridges, right? Because we just get a nice insulated box and we sit it on top of another box. But as this diagram showing, that's not always the case, right? There's elevators, there's service shafts, there's different reasons why we actually have to penetrate through that podium. And that's, again, where these kind of tricky details are going to start coming up. The downside of that is that we're already fighting for height in our buildings, right? We're fighting to get the maximum amount of floors within our zoning limits, but now we have to add additional thickness to that floor, right? So that transition from podium to up above, really ends up taking some space. We might cut off the access of our utilities from the ceiling below, and now we have a situation where we actually have to access utilities from the floor, which is, I would imagine, not ideal from a building maintenance perspective. And again, that continuity of all the shafts through the building. Our second option would be insulating below, and you can see in the diagram here that already, as you're dealing with the structure, this tends to get a little bit more complicated. So you're going to have to break that continuity of insulation as you're going from the top to the bottom, just to pass through that podium top. And then you're also going to have to deal with all of the structure of the podium itself, right? So if it's, again, not a completely flat, underside of your slab, you have to make your way through all of the kind of origami around that. The pro is that it does eliminate some of that additional building height, right? Essentially, you're kind of collapsing that height if that becomes, a challenge that or a constraint that you're already working with in your design. And a lot of the other kind of air sealing, difficulty around deck, et cetera, again, are important here. Okay, and one last thing about our foundation conditions is that we're starting to actually see the limitations of the current FIAS kind of perimeter thermal bridge analysis that we recommend. There is a new protocol out now for FIAS deep thermal bridges. It actually just follows ISO 102.11, and essentially it kind of widens the scope that we're looking at some of these thermal bridges, so we can actually account for, multi-story parking garages, et cetera. And it's all based on the width of your building. So the wider your building is, the more kind of ground that you have to model around this in your thermal bridge condition. And I can say that it has given me like pretty significantly different results in my thermal bridge analysis that I'm recommending this to all project teams to take a look at now. If you guys want the protocol, if it's not available on the FIAS website, let me know and I can send it. All right. So we established the ground conditions, the inside and outside spaces, as we're starting to build the building up. And eventually we get to our residential, our more kind of repeatable units, right? But we still have to have things go up and down in these repeatable units, right? So if you come from an architecture background like I do, there's a lot of really poetic language and writers about these vertical shafts. One of my favorite is Rainer Banham, who comes from University of Buffalo, talking about the Larkin building, one of the Frank Lloyd Wright buildings, and he calls it a stupendous piece of rationalized architecture and a triumph of industrialization. And he's really just kind of romanticizing this, like, this vertical transportation of a utilitarian aspect of the building, right? So I'm trying to make kind of a play for this, like how can we make these mechanical things, the very kind of mundane parts of buildings like trash chutes a little bit more interesting. To me, these, like, the detailing aspects of it is really what's like, okay, fine, I'll work on the trash chute detail today. Otherwise a past me would have tried to pass that off on an intern. So talking about these things, kind of in this mindset, specifically the things that we're really dealing with are elevators, egress stairs, trash chutes, and ventilation. I will say off the bat, elevators are easy, right? There's actually really not much of a reason to cut them out of the certified boundary. Some of the early multifamily buildings in FIA certification did cut them out, as well as egress stairs, and I would say probably to the project's detriment. I haven't really found much of a reason to cut these out of our certified enclosure unless the building already has such a low density that it's somehow needing to shave off kind of interior space. Again, usually not a fit for FIAS projects. The big thing to look at here is just to verify ventilation rates at the top of the elevator. Again, most building codes that we're dealing with now have minimal or no ventilation requirements at the top of the elevator shaft, so it's not really an issue. And this is kind of a theme that we'll come back to with trash chutes, who are quite the opposite. Egress stairs, very similar. The thing to look out for egress stairs is that even though it's part of your FIAS enclosure, and again, I would recommend just keep it as part of your FIAS enclosure, even though it might come all the way down to the ground floor. The thing to really look out for is that you don't necessarily have 68 degrees Fahrenheit heating and 77 cooling in an egress stair, especially when it's coming down multiple floors, right? So we're looking for thermal bridging potential, condensation risk, especially in these areas that we say are fully occupied, but they're not really fully occupied sometimes, right? So looking at the occupant density and the actual usage of these egress stairs can get a little important. I have seen many egress stairs that go down a couple floors actually failing condensation risk analysis, the ISO standard, just because it's really so far away from, the rest of the conditioning systems of that building. But again, generally elevators and egress stairs, simplest to just keep inside of the building. Now, trash chutes, the cousin of our elevators, are going to be a lot different, right? Because we need to maintain a negative pressure to get all of the trash odors out of the building. This, I would say, is like very much split right now as far as what practitioners are doing. Some people are literally cutting that trash chute out of the FIAS enclosure, right? So we call that like the donut hole approach. As you can imagine, there's a big challenge in that. And now you have a piece of your exterior enclosure on the inside of your building that you have to kind of crawl up to make sure everything's continuous. There's also liners that go in there, and it's trash. So, it's going to get banged up inevitably in the process. We do have, sorry, I kind of went to option 2 there, which is your all out, considering that outside of the FIAS enclosure. All in, we're seeing more and more. The all out, I thought, was kind of like a fear-based approach. that a lot of people use like early on in these big buildings. We do see more and more kind of brave practitioners. Probably Galen Stengel is one of them that's really kind of forwarding this idea of just keeping the trash chute in the enclosure. And he was very encouraging about like, yeah, it's possible. Like, let's figure out how to do this, which we'll go over in a minute. The interesting one, I call it option 2B, the far out. Like, just don't do trash chutes, right? Get like a trash service or something like that. I'm not going to give it too much lip service in this presentation, but there are project teams that are legitimately like pursuing that. So for the inside, and I think this is the more interesting approach that I would really love to try out on a project. Essentially, we just keep our simple enclosure around all the 6 sides of the box. We keep our trash room, the compactor room at the bottom inside the FIAS enclosure, and then the trash chute is inside the FIAS enclosure. The downside of that is we have to continuously ventilate out the top, right? Which is creating negative pressure. So what is essentially being proposed in a strategy like this is putting its own ERV at the bottom in that compactor room. So that relieves some of that negative pressure by making that a balanced space itself, right? So you have the bottom being a balanced space, and then you're dealing with really just the shaft. And you're getting negative, you're essentially sucking in air from all of the trash, the chutes themselves, right? So you have that airflow coming in from the individual floors, making its way to the top, and then out the top, right? So if we can actually quantify and minimize that as much as possible, really just sticking to the code minimum, depending on the size of the building, the density of the building, essentially you can determine that it's an energy hit that you're willing to take, right? So again, it's a trade-off decision. We're going to choose a simpler detailing process in the design and execution of this building in order to take a hit on the energy performance, right? This is a big pro when it comes to specifying the materials, et cetera. You can really just use like a more conventional trash chute setup, right? You don't need fancy airtight doors. You don't need aero seal to seal that whole shaft on the way up. Yeah, I think that's it for that slide. Okay. There we go. That's a little redundant. The second approach here would be cutting this outside of the airtight boundary. And this is actually what I have some not so great experience with. It ended up being fine on the projects I've done this for, but not without a little help from aero barrier and aero seal. It just gets really, really tricky to seal that shaft all the way up. So this is a positive because it minimizes odor transfer. It minimizes the thermal loss aspect, and also the energy loss of that continuous ventilation, right? It's just its own isolated kind of area. That creates a lot of problems at the bottom, at the trash room at the bottom, because now you need airtight doors again, right? I'm sorry, you do not need airtight doors for this situation, which is great when you get like these big, you know, rolling doors, overhead doors that are just really a bear to air seal. Okay. There we go. Now, the last type of kind of vertical shaft is really when we're thinking about centralized ventilation. So essentially, as we're dealing with both providing the same amount of ventilation down sequentially, you know, down a vertical shaft, as well as dealing against that stack effect ventilation, we need to come up with some sort of balancing strategy. So the taller the duct shaft, the more susceptible we're going to be to stack effect, even though that air is, you know, isolated in a duct. And primarily we're using constant airflow regulators to do this work, right? But there's still kind of smaller strategies within this this car damper strategy. So that's what we're going to go into here. There's a big debate out there, and this is where, I'm hoping James can, maybe chime in later, but about the use of automatic or manual car dampers, kind of self-adjusting car dampers versus manually adjusted car dampers, but also where in line in the ventilation system these are actually located, right? So in the first option on the left here, option A, using an automatic damper at each individual termination. So you're going to have more of these car dampers, right? But they're accessible right at the actual diffuser itself. Whereas a different option might be just using a manual unit floor to floor, right? And that allows you to manually go through as you're testing the building and commissioning the building to essentially kind of in a less detailed way, I guess, or a less nuanced way, just start to manage, every 10, 12 feet or so as you're going down the stack of the actual building. I'd say this is worth bringing up because even though some of these solutions are fairly obvious, the real challenge is in what is the proper testing of this? What is the proper verification of this? What are the proper piece of equipment to use for this? So I'd say this is probably one of the most kind of open questions for me reviewing projects with FIAS, to say, okay, as projects are getting finished, what is the most effective strategy here? And it might even just be down to team preference, right? So pulling in the opinion of the rater verifier, how they want to plan this whole thing in the beginning can make a big difference. And then there's always the option of just not centralizing your ventilation, right? So you're not dealing with this kind of shaft ability by even semi-centralizing your building, right? So at least in the previous version of the CPHC, we really talk a lot about, individual units in multifamily buildings, right? So unit by unit kind of ERVs, ventilation systems, or centralized. Right, so we're starting to see more projects that have these semi-centralized systems where they might just have a ventilation system per floor, or as we're seeing here, a set of 3 floors potentially, right? So it's based on the capacity of the ERV. And what's nice is we can start to overlay this with compartmentalization strategy for the building, or blower door testing strategy for the building. So now we're literally collapsing the work of the verifier who has to figure out how are we going to test this thing at the end. And then we have the design professionals in the beginning saying, okay, how are we going to say this is compartmentalized for Energy Star? And then we're really just bringing them together so that it's all kind of working in this very clear system from start to finish. So this is really my buddy Tony Lasanti, the FIAS QA QC manager, always like hammers this in, like get the verifier in early, get the verifier in early, and having them walk through some of these air tightness strategies with you, or even testing strategies, can actually lead to some great streamlining items in the design process. All right, coming to a close here. These ones I'm going to go through a little bit quicker. This is a lot of the same stories that we all hear, and I know you guys are all pretty experienced in this room at least. Exhaust ventilation. So the field of indoor air quality and exhaust ventilation is constantly changing around us. In the past couple of years, we've seen a lot of reports about indoor air quality and why we need to be direct venting our kitchen equipment specifically. We're dealing with things like what is the energy loss through this exhaust ventilation? How does that impact our air tightness as we're sealing our buildings? What about makeup air? Now we have to bring all this cold air in so that we're maintaining a balanced pressure. And then also in bigger buildings, what's the equipment even available to us? Heat pumps aren't necessarily available for commercial renting equipment. So we're, dealing with that market. I actually think it would be a great business idea to just lease heat pump dryers for commercial buildings, but that's again another idea. Our laundry exhaust, we're really looking at all in and all out. And this is where it gets really, really kind of interesting for me, because this is like a Very classic problem in passive buildings with direct exhaust dryers. In single family, we just put in a heat pump dryer, right? Easy. But that's not always the case, again, for larger buildings. So the probably most streamlined way we can do this is just keep it inside the passive enclosure, right? And you're dealing with a couple of dryer vents, you have to seal all of them. You probably have to do makeup air and bring a bunch of cold air in to balance the pressure in this building. We are starting to see some variations of this where it's like kinda in, right? So you have essentially, you still have that six-sided box being air sealed, but you create essentially a plenum space. And all this is doing is allowing that mechanical damper, the makeup air to come into the space, go right into the back of the dryers. So at least as that cold air is coming in, you don't have to precondition it because it's not actually interacting with the occupants. But it's drawn very simply here in this diagram. It's not that simple, right? You need to build the wall so your dryers can fit into it. It needs to be gasketed around the dryers. So there's a lot of kind of figuring out that needs to occur. But this is, at least from a comfort perspective, a solution that we're starting to see in some projects. There's a lot of questions about, well, why don't you just centralize your dryer vent? And then you just have one penetration through the building. That will put you into a commercial exhaust requirement, which is going to trigger some things like continuous exhaust, not using dampers, etc. Right? So we have to be careful with how we're designing these as well. There are some, again, projects, especially earlier on in multifamily buildings, I think kind of a fear-based approach here where just like, all right, forget about these washers and dryers. We're going to cut them out of the FIAS enclosure altogether. This makes a big difference in the certification process because you just don't have to deal with it, right? But from a constructability perspective, is this really the right decision, right? Now you're taking just one side of the box that you have to air seal and you're bringing that air barrier inside. You need to seal the doors into that laundry space. So it gets a little bit more complicated in order to do this. Okay, I'm gonna skip through the kitchen exhaust so we can make sure there's time for questions. I will say that note that you still require a continuous ERV exhaust in addition to your range hood as well, whether it's direct exhaust or recirculating. And I will say that the programs are actually changing, right? So we're going to see single family projects actually requiring direct vent in the not so distant future. So this to me is a really interesting trade-off because we're talking about energy performance versus occupant health, right? So I don't know. I'm still kind of struggling with it myself. Like, what are the real priorities here? Maybe it's a case-by-case thing, but I know that personally I would want to install direct vent range hood in my own home. So, you know, I think that's kind of one of the bigger challenges now is how to figure out how in multifamily buildings where we have 40, 50, 60 units that are all directly vented, how do we do that without incurring such a large energy hit that we can't pass our FIAS targets? So challenges out there. Last slide that I'll end it on with is just kitchen exhaust. This is like a big, we're just seeing cutting it out of the FIAS enclosure altogether to the point where I've even seen kind of larger communities, multifamily communities, just having a separate building where they have their commercial kitchen and kind of cafe area in it. There are options for heat recovery ventilation in a commercial kitchen, but tend to be cost prohibitive, overcomplicated, etc. So we have yet to see a certified building go through with that heat recovery in the commercial kitchen. Okay. All right, so that would be my last slide. Again, you know, there's a lot of different aspects or kind of more flexibility about how you define the FIAS enclosure, what's going inside of it and what's outside of it. To me, it's all about those trade-off decisions, right? So I don't think there's necessarily a right answer or a wrong answer for that you can say like kind of applies to all projects. but really balancing those trade-off decisions and figuring out what makes the most sense for the particular project that you work on and the team that you're working with is my recommendation. So thank you.
Ladies and gentlemen, we got to do round of applause. One right answer is bring the verifier team in early.
Yes.
Do that. That's always the right answer.
Yeah.
All right, we're gonna take questions from the audience and online, trading off. Anyone in the audience here want to start us off? And if you just say your name.
Yeah, hi, I'm Abigail Sabo with SH. I have a question about trash chutes. So you talked about option 2 or option B, I think you called it, where it's all out. And you said you tried many different things to get it airtight.
Yeah.
To get that shaft wall airtight.
Sure.
And you mentioned you ended up with AeroSeal, but I'm
Yeah.
curious what things you tried and how that went.
Yeah, that's a great question. Oh man, it gets technical quick. So basically we had this, CMU trash chute, whatever the dimensions were, and it was built all the way up and we sealed it with a liquid applied all the way up. It was actually built as kind of like a U. They sealed it and then I don't know how the phasing worked for that, but they did seal it with liquid applied on the interior. I think there was a lack of understanding of what that trash chute liner really does and how it connects to everything else, right? Because you have to build the physical, like structural chute, and then typically there's like a metal, like almost like a duct that lines it, right? But think about that. So now you have a duct inside this larger chute, and you have to consider how each of those ducts are actually transitioning at the trash chute door. So what we actually found in Lamora was that we had spent all this effort sealing the shaft. And then what we really needed to be, sealing the CMU shaft, but what we really should have been sealing was the liner, right? Because it was the liner what was connecting more solidly to the trash chute doors. And that was also just like the equipment that we specified. I don't know if that's like, a standard kind of detail. But what we ended up doing was we came back in, we actually used whatever the one not is, for not ducts, right? There's like one for aero barrier, thank you. So we used the aero barrier and we actually sealed that shaft wall. There are other teams who have sealed using the duct version inside that liner instead. Yeah. You're welcome.
We've got a question about, guess what, trash chutes coming online. So Ken Newhouser is commenting that there are non-passive building reasons for completely separating the trash chute and compactor room from trash from the enclosure. And he further commented that we need rodent and roach-proof doors and enclosures. No. We need to isolate the shafts for odor and other airborne contaminant control. Theoretically, the shaft is supposed to protect the building from fire and smoke. We can verify better than legacy visual inspection of these important functions by testing and verifying the airtightness, in my humble opinion.
Yeah.
What was the question?
I think it's a comment.
It's all good points though. And actually it brings up, Ken, thank you. Like fire resistance is a huge aspect in all of this. As soon as you're getting into these larger buildings, we're not dealing with fire. Well, in single family projects, you're really not dealing with it as much and it's not as important. And compartmentalization for fire resistance is a really big aspect of this whole conversation.
What's the question?
So my name's John with RDH. I'm a verifier over here. And so I really appreciate how you went into the whole Energy Star Indoor Air Plus stuff through your presentation. My question is, going through the design process, how do you balance or consider the different compliance pathway options? And how do you have those discussions and figure out what's the best method for this project?
Yeah, no, that's a good point. I mean, it changes honestly, depending on the team. I generally work as a CPHC and work with different raters and verifiers. So we have to kind of like reinvent the wheel, unfortunately, quite a bit. As a CPHC, I know there's like a couple, hot items that FIAS doesn't necessarily like keep under their purview, but they'll say, okay, but yeah, go see the Energy Star. So the big things would be material specifications for like indoor finishes, things like that, radon, EPA indoor air plus. So these are just kind of things that I typically will see that are based on the prerequisite programs that kind of fall through the cracks a lot. Like we call them like snags, right? Where CPHCs get snagged a lot. So as soon as I'm coming onto a project, whether there's a rater or verifier involved or not, like if we're doing like a feasibility study for Massachusetts, right? I'm looking at those things like right away, in addition to the energy model and looking at thermal bridging and things like that. But again, that's usually where like I've looked and I've spent plenty of time with the Energy Star programs and all the prerequisite programs, but I've never been responsible myself for filling out the paperwork, submitting it, going through the comments. And I know how much of a learning experience that is. So again, like as a CPHC, I want my rater verifier in, even if it's just for a couple hours during a feasibility study, because honestly, there's just too much to know about all the programs and different, versions of the programs in different localities to really ever feel 100% confident on my own. So I would rather establish the relationship early with a rater or verifier so that I know we can, transition a lot easier later on in the project. I don't know if that answers it.
Yeah, so I think more questions, like more folks like determining between like the ERI pathway versus the ASHRAE pathway and just making those determinations. You throw that kind of on the radar in those meetings, or is that something you're looking at from the CPHC side?
Yeah.
Which pathway works best for this project?
Yeah.
So you can then pass that along to them.
Yeah, just based on how I usually work with a rater verifier, I usually put that on them. To me, that's more of like a business kind of proposal, like how they want to do their work, whether they want to go with like an ERI path or an ASHRAE path. So I could work with either.
Great, another question, so moving on a little bit to ventilation, John?
Sure.
Got a question from Kurt Lamar. Do we know if FIAS is looking into the issue that stack effect has in high-rise buildings specifically? Because it seems to throw the upper ventilation system out of balance. And then he clarified, typically in centralized ventilation systems.
Okay. So the FIAS Tech Committee is definitely working on this and discussing this. I had an amazing conversation with Russell Richmond, who has actually done quite a bit of research on stack effect in tall buildings. And there's a bunch of different approaches to it. I'd say the biggest challenge right now that FIAS is trying to tackle is air tightness testing and the standards around that. We tend to lean on the Air Barrier Association, but the FIAS protocol, it's unclear sometimes, like how it overlaps with that and how it doesn't. As far as the stack effect in central ventilation, there's not really any work being done from FIAS necessarily. I think we're more kind of like leaning on practitioners, like you guys in the room, to get real world experience and integrate it that way.
All over there. Hi, my name is Matthew Coulteri from SGH. John, you mentioned you're 10 minutes outside of Massachusetts, so maybe this would be a question for the room, but if you have input, I'd love to hear it too. The Passive House certification, we've seen the highest rise on multifamily projects, obviously, because it's required here. For multi-use, mixed-use buildings. So much of the time, the level 1 or commercial spaces that are included in multifamily buildings are core shell fit out with the team. And the way the code is written, there's a section for here's what you have to get a building permit. Here's what you have to get a certificate of occupancy. And for the Passive House compliance path, you need full certification for both. So when it's an unfinished space for the mixed use, I understand we can take that all the way through design certification with unfinished space protocols, but navigating with the team, okay, once we do have a tenant, once we figure out what the program of that unfinished space will be, there's going to be some, not necessarily restrictions or limitations, but considerations that fit out needs to be aware of very early on in the core and shell process from the owner developer side and from just the code compliance path.
Yeah.
In general, so I'm curious to hear others' experience of when we start carving up some spaces in the mixed use, how that's affecting the code compliance path and particularly for the buildings that is required.
Sure. Well, I'm definitely curious to hear what other practitioners have to say in this room too, but I can say from like a FIAS certification perspective, I'm sure you can come across, there is a protocol for, you know, non-programmed spaces essentially, and it is conservative, right? So I agree, it's easy from a design certification perspective because you're just building this box and it's going to be a passive house and it has these conservative targets, but there's a real need to, as you know, the actual program to really refine that to make sure that you're designing based on good building science rather than just an arbitrary certification process. Generally, like in the larger projects that we're seeing, like a lot of the mixed use projects that are coming across the FIAS-Q, it's fairly predictable, like 425 Grand Concourse, they knew it was going to be a grocery store, right? So it's a question of who the owner of the grocery store is, not is it a grocery store or a nightclub, right? Two very different ways of occupying a building. So TBD, I guess, is the best I can say of right now, but I definitely recognize the need to refine as you get that real client.
John, we've got a question. Can you talk a little bit more about the implication of designating an interior laundry room as outside the boundary? Ken is not specifying outside which boundary, I presume entirely outside all of the boundaries?
So it's really outside of the airtight boundary is going to be the most important there, Ken. Because it's so to be outside of the FIAS enclosure, it would need to be outside of the airtight boundary for the blower door test. But you still have to meet your code minimum insulation requirements, and it probably doesn't make sense to step down on your insulation just for that strip of building. So you're kind of separating your airtight boundary and your thermal boundary at that point. And then having to deal with all these kind of interior turns from an exterior wall to an interior partition. So it gets pretty complicated. And I think any team that we've seen do that would agree that it was fairly complicated and probably not worth doing again.
Last two questions.
Diane Tubbs, PCA. I was curious if you have any rule of thumb guidance on when stack effect, like whether it's building height or number of levels, really does become a design factor and should be factored into the conversation.
I was asking this exact question to everyone, like, what is the threshold? Like, is it 5 stories? Is it 20 stories? Unfortunately, it's just like, it kind of depends. It's going to depend on the climate, the time of the year, what's the difference in temperature between inside and outside. There's so many variables that factor into it. I'm sure an engineer would have like a much more precise answer, especially for like that centralized ventilation system. But this is also something that's like very much factored into elevator design and, you know, a lot of these kind of traditional vertical shafts anyway. Again, going back to my conversation with Russell, he was like, you don't have to worry about it in passive buildings, like because of that really tight enclosure. Granted, again, you can always open a window or open the double doors to the lobby or whatever, but generally it's a lot more controlled. And that's really the most important thing when kind of working against stack effect is just control. Yeah.
Last question.
So Debbie Chambers is asking about kitchen ventilation and specifically makeup air dampers, and asking if there is a less leaky direct to outside damper that exists that you might know of. They usually open based on the airflow and the pressure when the hood is running, but unknown how tight the damper is when the hood is off, which is most of the time. So especially over time.
Yeah. In the single family world, Kramer Silkworth, Balcraft Engineering, he has a go-to makeup damper. It's a low voltage wire that's going from the range hood to the damper itself, and then it just has a magnetic seal. So it seals on its own, and then it gets that like extra seal with the magnet. So I've had fairly good success with that. Most of the single family projects, I start off with direct vent dryer and direct vent exhaust now, in the kitchen. So, we're still meeting targets and passing blower door tests. I apologize, I can't really speak to that in multifamily buildings though, like larger buildings.
Well, if people have more questions, come and ask John directly, but for now, we're just gonna give him a big round of applause. Thank you so much, John, and if you haven't signed in, please make sure to sign in at the table out there. Thank you so much for coming. Look out for more PHMass events in your email.